parameters will be different. However, we have surprising things. So if you take mean of x, so for each of them it is same. If you take variance, we know the definition. So this is exactly same, mean of y. Up to 2 decimal places it is same. The variance is also same. Correlation between x and y. Up to 3 decimal places they are same for each data category. Okay. So we should be like surprised. The data set looks like different, but if we apply the classical method, we are getting same results. Then how to distinguish that data set? Okay, so that may say that okay, let's try to plot the data set in the X also. If we do that, then we get this picture. So pictures may look like different, and actually it is looking different. So how to capture the information? Now, having one single class of data set which gives the same kind of statistical information, from there somebody can produce as many different class of data set which looks different, but they give the same parameters, statistical parameters. Okay. So what to do? So it gives the idea, okay, we should have different concepts. So what is the idea? So if we have some abstraction, then what we should find next? So can we have something more advanced shape? So that shape was like regression line and some other shape. And so can we have something little bit more advanced? Okay. Can we have some other question also? So given this data point, whether we can have more information, whatever information we are getting, can we have more information from that? I just put the name neural data because from there we can have many networks. Okay. So our brain network, it has, if we subdivide and how they are working, we will get million networks because we have million neurons. Right? Okay. So the question, I mean, if you want, you can try to make more questions also. So these are the basic questions. Now to answer this, how we can answer it? So that means what we discussed in the beginning, the topology discussed about the properties of the shape. So if we want to have advanced shape, so that means we need to bring back some topological notion. Okay. So this is another way to get some graph. And as you notice that if we are having more nodes and more interactions between them, then we will get more complicated data. But this gives a graph. Right? So in the previous case, what it was, it gives a graph. But we want to have whether the network has some shape. So can we have some more topological tools to answer those previous questions? Whether we can have some shape. Okay, now up to this, is it okay? What is our goal? Okay. So we have some data set, and then we want to have some shape of the data. Okay. So around 2000 or 2002, some people they started to answer these questions, and it has some components which are known as persistent homology and persistent module, persistent diagram, and they found that it will be much more useful than whatever result we have. And that subject is called topological data analysis. So roughly I will say what is the pipeline, then I will discuss it broadly. So first thing is we need to get some data set. So that means it is a finite. Okay, we can have infinite, but whether we can handle it. We cannot do the computation very nicely. So we take the finite set. So if we have finite set, what does it mean? See, it's just a point, collection of points, right? So when that collection of points will be meaningful, if we consider these points in some metric space. So that means there are some activities between. So that metric is important. So it doesn't matter. It is not always the case that it has to be the Euclidean metric, but some other metric also. So having that metric, we can have some properties which will give the graph structure. Okay. So this, having that graph, what we can have some algorithm to have filtration. Yes, it simplifies complexes, so another new terminology which I will introduce. So from the data set we have graph. From the graph it will have simplified complexes. For the this is higher dimensional generalization of the graph. And from the simplified complex, so if we have simplified complex, we get the topological object. So corresponding to data, we get the simplified complex, that is topological object. And now topological data analysis means we need to study that object topologically. Okay. So if we have this topological and geometric information from the data set, then we can build the homology. So this topological or geometric features, it does not need to be always homology or homology, but some other things also you can think about it. People nowadays they are doing like topological complexity, persistent topological complexity. That is also another thing. I believe that personally, I believe that that will be the correct way to do the topological data analysis. This is one way. So there is some other ways also. But I choose this way because there are plenty of problems to say. And the other one is still developing. Okay. So now if we have that information, what we want to do? We want to do the computation. And how we can do the computation? We have to put that algorithm in a machine language, so that the machine will do the work. So the fourth stage is for that. So it has to put in the machine so that it will give the answer. So that means it is related to the machine learning problem. Okay. So here we can have this. So what machine learning models we should have so that we will get an information about the data. Okay. So I took these 5 lines from this paper. So this is an interesting paper which gives a very brief survey about this data analysis. Is it okay? So we have 4 components. One is data set, one data set to how to break the graph structure, from graph structure meaning like with metric. So if we have having metric, then how to get the simplified complex. I will introduce all of them again. And then if we are having simplified complex, that means we are having a topological space. Now for the topological space, we can do whatever we want from the topological side. But that will help the topologist. What about the applied people? So applied people will be happy if we can do machine learning. Then you tell your coding that okay, I am doing this coding and this will be the fastest coding or the fastest algorithm. Applied people will be happy. Okay, so n simplex. N means like positive integer. So this is nothing but convex hull of some points which satisfy some properties. So what is the example is like closed interval, a lot of things like triangle containing the interior side. That is called 2 simplex, and tetrahedron is 3 simplex, like that. But mathematically we can just say that okay, this is the definition. This is satisfied this condition. The convex hull then plus 1 new point in the general position is called the simplex. Otherwise you know that if we are given finite set, then The convex combination of the finite set is like convex half. Okay, so this is the definition. So definition, if we do little bit geometry, it is one zero dimensional thing. So this is like that. The definition of n simplex, okay? Okay, why n simplex is important? Because you can see tiles everywhere nowadays. So if you see the floor, you have tiles. The tiles is like rectangular kind of thing that you can make it triangle. So if we are having some object and locally we want to know, so how we should, what will be the best process to know the manifold, locally or globally. Locally, if we can fit something very nice, so what is the nice object? This is the nice object. So we fit it together so that it will be covered by this type. So type is this n simplex. And that kind of things is called as simplicial complex. So we define the simplicial complex. So it is nothing but it is a collection of n simplices or any dimension, zero dimension to some n dimensional. If it is finite dimensional, it should satisfy some property. So that means the overlapping should not be like this. It should be like on the boundary. Otherwise, if it is overlapping in a bad way, then you cannot do the calculation. You cannot say that, okay, how much overlapping is there. But if it is overlapping very nicely, then you can say that, okay, its property is calculable. Right? You can do the computation using it. Okay. So this definition, okay, maybe many of you didn't see this. I will pause for a few seconds. Maybe one example is good. I will go back and forth. So what it is doing, this triangle and this edge. So if you see the intersection of this, it is a face of both. So here, if you take this triangle and this triangle, so they are intersecting around this edge. So if it satisfies very nice properties like this type, then we say it is a simplicial complex. Okay. It's okay? But the mathematical definition is this. You know, what I feel in mathematics like is good because whatever we observe, we try to fit in such a way that we can apply it in many places. So, we have some observation, putting the tiles together, we made a light, and we know English because our ancestors were like quasi-British, so we know English. So we just write some English sentences, meaningful English sentences. Okay. It's okay, definition of simplicial complex. So we just need to remember that tiles are putting together very nicely. That's the simplicial complex. And if we do it, it will look much more nice. Okay. So what can we see from here? Suppose nowadays what we see, wherever we go, some structure will be there, which looks like this. So you can put it. So mathematically, it's the same thing. As I told you, whatever I see is like topology, nothing else. And now some, my friend from analysis, they may say that, oh no, you need to give the exact map. Okay, we can give it, but for the time being, we are not interested in that. So now we have interesting concept. It is called simplicial homology. So it takes time to digest the meaning of simplicial homology, but I will try to go very slow. All of us will know ring, concept of ring, right? Or module. So what we have, this is a simplicial complex. So what does it mean? It is a collection of simplices which satisfy some conditions. Okay? Okay. So we take these I-dimensional simplices, we just consider them as a like variable. So this AI, and we take the formal sum. What do you mean by the formal sum? It runs over all the index where the index set is finite. Now if we consider This like, okay, if it was finite to many, x1, x2, xn, we could take the function of x side. So it looks like linear polynomial. So this is nothing but like linear polynomial kind of thing. The coefficient is coming from some field, I mean ring. Here is a ring or field, whatever you see. So this sum, finite, this is a finite sum. So it makes sense, right? We should be clear about that. Is it okay? So what structure it is having? It is having a ring structure here. So given a set, we can take the formal sum and the set of elements, because if we add two of them, then again it is a formal sum. So, and if we, okay, multiply by the ring element, it is again there. So it satisfies the condition of the group. Okay. So this group is called like chain complex, IIT chain complex. Okay. So I is coming from the dimension of this simplex. So what does it mean? So n simplex, we have n plus 1 many points which are in general position, meaning that if you take n many points from there, they don't belong to the affine hyperplane which has dimension less than n minus 1. Okay, that is the definition of general position. So is it okay? The chain complex, I chain complex, okay, we just took the set of all I-dimensional simplices from this collection, then we made the formal sum, yes, with coefficient coming from this group, and we said that okay, we take this, that is called I chain complex. Okay, so what we can have from I chain complex. Now look at here. So if we have a simplex, then it has a boundary. The boundary consists of faces. Right? Those are like, again, codimension 1 simplices. But how many boundaries are there? If we are having n simplices, then n plus 1 many boundaries are there. So we should have a orientation on that set. So this is A is I simplex. Okay, so this is I simplex. Now how many faces will be there? And codimension 1 faces. So if we omit one of the vertex, then we will get all the faces. So how many will be there? I plus 1 then. Now what should be the connection between them? So the connection, the relation among themselves is given by this relation. So if you say boundary, you could say that, okay, we'll take the sum, but it will not help us. Because if we take the sum, it will not be interesting. So what will take the alternative sum? So first we have to consider one orientation. Since we take the finite simplifier complex, we can give an ordering of the vertices of the simplifier complex, which will induce an orientation on each simplex very nicely. And then we can have this formula. Is it okay? So what we are doing, we take IF chain complex, elements from IF chain complex. Okay, this we can think of a basis. This is the basis. So from here, we have to define in our set. So how we are defining this way? We may think that okay, there are other ways also. Yes, we can have many other ways, because from simplex to its boundary, while we have to consider all the boundaries, we can take the partial one and we can try to do whatever we want. However, the interesting thing will not happen. What is that? The composition of these two may not be zero. But if we take this way, the composition of these two maps, boundary map, it is called as boundary map, the composition is zero. Because if you apply the boundary here again, then you have to commit some element from here, then I do some calculation is there. It will say that the composition is zero. So that means then you have to be like that, Okay, that's a good question. I like it. More questions should come. Okay. So whether it is the depend on the condition or not. So how you can check that? We want to take like two simplex goes to one simplex, then one simplex goes to zero simplex, and you can check that whether you should have this. That's good. Thank you for asking. So what happened? So if I will answer your question. So if the composition of two maps, so this is homomorphism. As a module homomorphism, so this is a module structure over R, and this is a module structure over R. So as a module homomorphism, this one I will take 2 minutes because it's not that much familiar to us. So if the composition of two homomorphisms are 0, then what happens? This image of this one is a submodule of the family. Okay? That we studied in the homomorphism of group or something, or homomorphism of rings. So this happens. So therefore, since it is a module, so it is a normal subgroup of the quotient module makes sense. So that quotient module, we are saying that it is the IF homology group or the simplicial complex. Okay? Is it okay? The definition of IF homology group. So what it has, X is a simplicial complex, and then we have this 10 complex. So 10 complex is generated by the IF synthesis, I-dimensional synthesis. Then we have a map from I-dimensional synthesis to I-dimensional synthesis. So this is content. So if it is the IF synthesis, what should be the map? So this map is this. Question 10. If the composition is 0, whether it is equal to only, so we will check it little bit. Is it okay? The definition okay? Up to this. This is little bit complicated. Okay, I feel complicated because it took me to realize why the definition of the homology group should be like this. It takes some time for me to take it once. Okay, so I go a little bit. So how we understand mathematics? By doing computation. So sometimes I tell my students that when we are in high school, we have to do problem solving, so many problems. But when we come to BSc, then we think, oh, we did too many problem solving, we don't want to do. When we come to MSc, it becomes more or less. I don't know why. For me, it becomes more and more because I didn't know many things. But the students follow that, okay, I don't want to do the calculation, but here let's do some examples. So we take the boundary of two simplex. So it's like boundary. So you can see what it says. So what will be the 0, 10 complex? That will be generated by only 3 because 0 dimensional. Okay. So and the 1 10 complex will be generated by the edges. So these are the edges. So now you can see we put the oriented edges. So this C1 is asymptotic to Z2. Z2 means 2 generators are there and overflow. Okay, here the ring we are considering, that is there. So dynamic will fit. Okay, why this is 2 here, why this is 0? Because in the boundary of triangle there is no other higher dimensional synthesis. So the chain complex automatically becomes 0. So the chain map, it will be like, if you just know this map very well, then you can get. So what is this? So if we take this one, so by definition, okay, now the question is, what it has to be? Whether V1 plus V2 or minus. So if you take this plus, then the composition will not be 0. So therefore it is like this number. Some other coefficient, if you put some other coefficient also, like 2V1 minus V0, then also the calculation will say it is not 0. therefore, that is the conditions we have the composition of this boundary map is 0. So what will be B0 then? It is image of delta 1. So what is the image? Image is generated by this differences. So if we take, if we add these two, then we get B4. So these three are not independent, so they are dependent. And two of them, they are independent. As a module, they are module basis, they are independent. So it is two-dimensional circular. Okay.
Why are we looking at that?
Okay, that's a good question. The thing is,
That is geometrically
that is another way that why? Oh, good, thank you for asking me. So, if we have some topological object, what we want to know? So, up to homotopy, how it looks like. So, for example, if you have, bandage, you have this donut kind of things. So how topologically it looks like, you can shrink it and you get circle. So it has a hole. What about the higher dimensional case? So if you take our football, not like American football, but like European or like Indian way of thing, it's like a sphere. So it has hollow things. It's not. So you can have solid also, but if you take solid, up to homotopy, it will be like contact cable. So when we are saying that the composition has to be 0 in the sense, if we have something, whether this bigger set is affected, so meaning that whether we have some dimensional voids there. So how to measure that void? The question is how we can find that void. For example, if we take sphere, then is there any one-dimensional set there which is not contracted? So how to measure that? Now how we can think our sphere? We take the boundary of the triangle and we take the suspension. Then we get a simple complex structure. So from there, if we try to do the computation, the main goal of the computation is whether it contains some void, right? Whether it is empty or it is contractible, or how much it is contractible. So because of that, we have to have that condition. The composition has to be 0. So that the void things and non-void things, it will be, and the contractible things we can contact in the process. So the boundary, if you have contact, then how many void things are there, it will contact. So that, thank you sir for asking this. So it says the collection of some sequences, right? And there are some. So that gives some topological object. But other extra things we are filling here. So it will say the measurement. So like if we have this circle and this one, if we fill that, we will get the measurement of the part. So how much it is there? Okay. So that's why we needed the composition. So how many? So in ith dimension, how to measure that one? Because of that, the composition has to be 0. So that means here, this is a sub, it is like this one. So it should not be, it should be 2. So it should be 2. And the exact value should be remaining. So this measures that how many voids are there. Let's go. Okay. Good. So here it is two-dimensional, not only subgroup, but it is a direct summary. Okay. So this is two-dimensional, and if we consider the zero chain, so that will be generated by all these three. So this will be isometric to set. So what will be the zero homology? It is nothing but Z0 cosine by B0, so that is it. Actually this is most of the cases, and this counts the number of connected components. So if it is connected, if the simple cell complex is connected, then it is always Z. So what about Z1? Okay, we take a one cycle. So one cycle meaning like formal sum of that. So we take A is V0 V1 and V1 V2 and V0 V2, and then what condition we are having that okay, we take this sum, but whether it creates some one-dimensional object or not. Okay? So it creates one-dimensional object. If we satisfy this one, so if we have that, then we get this one. Now we have this relation. Now we can easily check that from here what should be the value of L. So L has to be equal to L, L is to be minus L, so this minus sign. So because of that we have to take the alternative. So that's like okay. So any one cycle will be looking like this. So that means the one cycle is generated by this one. And what is B1? B1 is coming from image of C2. But C2 is know that 0. So if you have a 0 module to some other module, the image will be always 0. So B0 is 0. So the percent is 0. And other homology is like 0 because the cycle, the dimension cycle, automatically is 0. Percent is like 0. Okay. So that is the computation for the homology of cycle. And you can see it takes some time to do the calculation. Now if we have to do some little more complicated things, so that natural question will come, what is the homology for L-dimensional scale? So if we take it as a boundary of L plus 1 simplex, then computation is little bit difficult. But is there any other way to do that? Then the answer comes from differential. Is it okay? Concept of homology. So what we have data set, from data set we have graph, and from graph we have simplicial complex. I didn't say that how we can get the simplicial complex, but we will discuss. Before that, we will discuss the concept of simplicial complex. Okay, now the important part of our life or this talk, it says if we are given data set, then how we can get the simplicial complex. So what we are considering that this is a subset of some metric space. Some distance function is there. It can be Euclidean metric, it can be other metric also. There are several ways to do that. We know several types of metric, right? So this is a subset of this. So if we are having a metric, then we can have this kind of subset, which is like a ball of radius epsilon around this. So if we have two balls, this one of k meaning balls of radius I as epsilon, and if their intersection is non-zero, then we can say that okay, we will consider this set as a k minus 1 simplex. Because we are having this set, and their intersection 0, so that means it is like filled up, so the concept makes sense. We can define it. But whether it will be meaningful also. So in the next slide we will see that it is meaningful in some sense. Is it okay? So this is called check complex at level epsilon. Is it okay? So from data set, how we get a simplicial complex? Now you can say that how to determine this rho. That is the important part in our machine learning. So if we have to do the exact calculation, suppose we are having 3 points or 4 points. Right? So if we take it as a square, then whatever simplicial complex we will get at epsilon level, if the 3 points are very near and 1 point is very far, the corresponding simplicial complex will be different. Therefore, this net case, choice of mistake is very important in our data analysis. If it comes very naturally, then it's okay. Otherwise, we need to find a method. Okay. So, in topology, what we know, if we are given a metric space, so that means it is a topological space and it has open subsets. So we can define open subsets. So we take the collection of open subsets. If the open subset satisfies the similar condition, oh, there is a mistake. So it will be U I K. So it has to be U I K. If that intersection is non-empty, then we will say this is a simplex. Okay. So we will take this collection of simplex and we say that this is a simplicial complex for the mark of this covering. So what is the information connection between this simplicial complex and the previous complex? So that is called the mark theorem. So if we take this collection of open subsets from this topological space, which satisfies this condition. That if we take any finite collection of open subsets from collection from there, their intersection should be contactable. Now it comes the concept of contactable. Either it is empty or contactable. So, like if we have this open space, this theta, so this is contactable in the sense like we can push it to a point. Okay? We can sink it to a point. However, if the open set looks like this, and these two, so this is U1, this is U2, their intersection is with this two. So we are not considering this part. This is a part. So if you have this kind of situation, then it is saying the space M we took, that is homeomorphic to the geometric realization of this null complex. So now it looks like simplicial complex, it has nice structure, but topology may be like complicated or crazy. However, they are like homotopically equivalent. So what does it mean by homotopically equivalent? It's like we have map from X to Y and G from Y to X such that this composition is complex P is homotopic to identity of Y, G complex X is homotopic to identity. Okay. So in other sense like their topological properties are same. Okay. Is it okay? So this is important. So from the data we get a simplicial complex and we can say what we can do with that. It's okay? So this is important theorem in the topological analysis. Okay. So what we are considering is check situation. So what does it mean? So we took some point set, so that means data set, and the metric space in the data set, and we will take. Okay. So if we have some shape like this, suppose the shape of the data is like this. So how to get it? So we will get this one using check complex for the computational purpose. But if we take the neighborhood, then what we will get? It will fill up. We will get like tetrahedron kind of thing. But we should not be up to that. So how far we should go? So that means what choice of this epsilon 1 or epsilon n we should have. It depends on the shape of the data. But how to determine that? Our goal is to determine shape of the data, right? So we have data set, so we will make these complexes one by one. So the difficult part is to say or find this epsilon 1 such that this set will give the exact shape of the data. That is one difficult question in topological data analysis. If we get this, okay, this is the data set, and if it happens, then we are happy. But how to determine that epsilon? Okay. So one of the good problem, how to determine that one. So this is an example. So I just took it randomly. You can see that, okay, if I take these two near ones, and this is little far, then we will get this set because we are considering open doors there, and they will intersect these two open doors. will intersect before this here intersected. And the intersection is like contact to it is the Euclidean metric. So we get this one there. Now this gives the full sequence. But we may have to stop here because data set may be up to this extent. So topologically, and this construction is not saying where to stop, but it gives the construction. At some point we will get the data set. But how to build the data set from the simplicial complex from the data set. So there are some algorithms. It is now algorithm that is very well known, that is called MADRAS algorithm, and computer can do it. Okay? So what it is doing, this data set is like this, so if you get some cluster, before that also there is another method, it is same, they use it, that is called like principal component analysis. So if the data set is very huge, they will take little, so they will do the dimensional reduction, they will come in little bit lower dimension, and then they will find this clustering. So they do this clustering, so there are four, this is a very easy example. So 4 clusters, each cluster will give one node, and if there is an intersection, then there is an edge. So this algorithm says that what should be the graph. Okay. So now we have graph, and if we know the metric, in 2 slides before that, we saw that if we are having metric, then we can have a filtration, check complexes. And now, if you love the computer language, then the question will come, how to put that information in the computer language. Okay, topologically we can do, but how to make it in computer language. I think for the check complex it is there, and this complex also there. They are related. Okay. Okay, up to this, okay. From data how to get the graph, and graph how to get the simplicial complex. And simplicial complex is in topological space. And the easiest things to compute in topology is the homology group, not the homology group or canonical group. So that is because of the definition. And what it finds, as Professor MADRAS was asking, that what it means. It means that how many voids are there, we want to find out. So that is the homology, computing homology gives the answer. Okay. So, is it okay? Now we can try to, if you love computer language, we can try to find out some coding which will say how to find out the second homology or third homology of the simplicial complex. And then the question will come, okay, you will have algorithm, whether the computer can compute it, meaning like how long time it will take. Whether you can give the fastest algorithm or longest algorithm, all question will come. Okay, so we have this RF at RF stage, so that means this R is epsilon. At the RF stage we have this simplicial complex, check complex. So if we take the kth homology of that is called as kth persistent homology at the RF level. Okay, so we know the concept of homology, we know the concept of check complex, and we are just defining it. Okay, this is the kth homology of the homology group of this check complex, RF level check complex. So what it measures, so why R? R is like when we are moving, that epsilon we are moving, right? So we have data, we wanted to understand the data set, so we try to have the simplicial complexes from there, but how far we can go. So if we go slowly, that how to determine the shape of the data? By computing its homology. But how many holes are there inside the pixels? Okay, so that will determine the shape of data, because after some time it will be up to some like k-dimensional sphere can be fit into that, which cannot be contacted. So that is measured by this kth homology. Is it okay, the definition? So that is the good thing. And right? 2, 3 minutes? Okay. So is it okay? So that is called like persistent memory. Why is that? Now, so sometimes one hole will come like right. Now, after first time, it will be filled. So that means it will be contactable in higher dimension. So that is called like birth and death. So that birth and death we can represent it by some bar representation. So that is those barcodes are called like persistent. Okay. And persistent diagram also will come for a given data set and the situation. One can record this interval as a persistent barcode, and then that the 2 points B, D it can be put as a point. If that point is very far from the diagonal, then we say that it gives the real feature of the data. So that is that file that in the data set, in the set of the data set, it is remaining for long time. Okay, so we have data set, so this is C0, and then what bar is what this means. So if you have this one, some of them are remaining and some of them are disappearing. There we have 3 holes, there we have 1 hole, so it is remaining there, and there is something there. So corresponding to this observation, we will have this point. So this represents path and death. So here is death and this is path. So that is known as path. There are some good features. If this point is very far from this diagram, then we say that the data set is kind of so that means the dimensional height is there. Okay. Okay. So I will discuss what are the concept and methodology in briefly. So it is like we take the shape or we try to understand the shape of the data point cloud or the point cloud. This can be multi-dimensional, whatever the shapes are there. Okay. Okay. Then from that data set, we take the persistent homology. So it says that how the shape of the data set behaves. Okay. Then we get this one. So this is important because then we can compare. So for example, if we are having normal cells, and normal cell, then no need to study. But at least we need to study and see that what are the properties it is having. And if you have cancer cells, then also we need to have some collect some data and compare them. So how we can compare them? So we will get 2 different persistent diagrams, and there are some methods to compare these 2 persistent diagrams. That today I am not going to say because so many things. On matter observing, it gives like it creates one-dimensional graph. So how many questions can be? So it can be applied in many places. Okay? If it is very noisy data, sometimes it is difficult to understand using classical statistical method. Like if you have data set in a circular way and you get a regression line, you cannot get more information, you cannot compute that much. However, if you study this topological data analysis, you can say that okay, this shape is the property of data. So we use dimensionality reduction such that it will not change the property of the data, it will not change. So it is now applied in many places, in genomics, material science, image processing, and here you can see that how many open problems you will get. We know that topologically we know the algorithm, but how to fit it in the machine language. And whether the fastest, how much fastest it will be. It is amazing. So we have topological side, what type of metric we should choose, then if it that is crucial first, and then what will be the homology calculation, and if you do the homology calculation, what are the methods? So doing calculation for first, second, third, I know that it is known. But if we have to go, I don't know any other algorithm which can be fit and check in the machine. So that kind of things are there. So many almost everywhere these are happening. So what they are doing, they are comparing what is the differences between their persistent diagram. Okay. And the bad part is, in the sense like if somebody wants to do it, he or she have to know so many things. Topology, graph theory, and the places where you can apply, and the tools also, this C++ and Python. So during my MSc, my teacher wanted to teach me C++. When I saw the algorithm, I said, "Sir, this is very easy, I don't want to do that." But now I can see it is not easy, it is also complicated thing. If you have to use this one. So you can see, if you have to do the topological data analysis, you have to be also robust, like the application. So many things you need to know. And there are, some references I just included. So it started around 2002 or 3, then many applications are happening. Gunnar Carlson and one of his students, he was doing some other things, and then Zamordi, I think Gunnar Carlson and Zamordi, they started. It was around 2002 or something. But in this paper, if you read this, it will be very difficult to understand. But you need to read so many papers to get the idea. Okay. So, several applications. Here you can see in the online network, cryptocurrency market, maybe here also some other, how is that? Industrial challenges. So we love to have industry in our mind. There is like something related to black hole images where we can apply some medicine studies, and here like neural network, landscape. So many areas, it's been like very hard. In the last 25 years, and in the beginning 10 years, it was going very slow, but now it is blooming like anything, like here the cancer, digital marketing, information space, functional data analysis, this outcome. Again, my problem is, if I have to do this, then I have to know the other areas, like biology, which I don't know. So that becomes like problem. So the biomolecular properties prediction. However, if you go something such as so many applications, and thank you for having me.
Soumen sir, for the insightful and enlightening lecture. We now invite questions from the audience.
Hello sir. My question is that how topological data analysis is effective in detecting adversarial attacks in cybersecurity, as it is a concern in nowadays so many times. So how we can tackle it?
Actually, it depends, but what problem, that tool is that I just said, that if I have to apply, then I have to know that real world biology. But I don't know what is happening in cybersecurity. By name, I think like, whatever, I mean, it concerns about security, right? Sorry, that subject I don't know. So, any other question related to that?
So it was actually a concern with our country that in 2023 aims ransom attack. So that's why I'm asking, because so many hackers from the different countries try to hack the systems, and so that's why.
Whether we can detect it.